What's up everyone, Lakonde Mwila here, back with another video, and we're talking K8s. One of the features that draws people to Kubernetes is its ability to scale automatically. And a big part of this video will be highlighting how a tool like Karpenter is designed to provide the exact compute resources for your cluster based on your pod requirements. No more, no less. But in addition to that, there are scenarios where you might have some specific or advanced scheduling requirements for your workloads. For example, this would be pod affinity, pod anti-affinity, and volume topology awareness. So in this video, I'm going to focus on these Kubernetes scheduling features and how Karpenter can support such requirements even when optimizing your cluster's compute resources. Let's start by talking about pod affinity and pod anti-affinity. These features allow you to apply rules that inform the Kubernetes scheduler's approach in deciding which pod goes to which node based on their relation to other pods. Similar to node affinity, this can be applied in a hard or soft approach, which will tell the scheduler whether certain rules are required or preferred, and it will act accordingly. Pods that have a required rule will be placed on a node that satisfies the relevant constraint, and pods that contain the preferred rule will be scheduled to nodes that match the highest preference. These rules are applied in relation to the topology of your cluster. The topology of your cluster essentially refers to the arrangement or layout of the physical components and resources of your Kubernetes infrastructure. Using topology spread constraints, you can apply parameters that determine how the pods are distributed across topology domains such as nodes, regions, zones, etc. The pod affinity rule informs the scheduler to match pods that relate to each other based on their labels. So if a new pod is created, the scheduler takes care of searching the nodes for pods that match the label specification of the new pod's label selector. In contrast, the pod anti-affinity rule allows you to prevent certain pods from running on the same node if the matching label criteria are met. Let's think about some use cases for this. For starters, pod affinity can be beneficial for pods to co-locate each other in the same availability zone or node to support any interdependencies and reduce network latency between services. On the other hand, pod anti-affinity is typically helpful in preventing a single point of failure by spreading pods across availability zones or nodes for high availability. For such use cases, the recommended topology spread constraint for anti-affinity can be zonal or based on a host name. And this can be implemented using the topology key property, which determines the searching scope of the cluster nodes. The topology key is a key of a label attached to a node. Now, using Karpenter, we're going to be able to make sure that the new compute provisioned for your cluster will satisfy these pod affinity rules as workloads scale, without having to configure any additional infrastructure. Karpenter is going to track unscheduled pods and will provision compute resources in accordance with the required or preferred affinity rules defined in the resource manifests. Let's take a look at this in action.
All right, so I've already provisioned a Kubernetes cluster in my AWS account, and I'm using Amazon EKS for that. In addition, I've installed Karpenter. If you're brand new to either one of these components, that's totally fine. You can make use of the links that I've added in the description below. It'll help streamline the process for you to know how you can get started with either one of them. In my situation, I prefer to work with Terraform to provision my Kubernetes clusters. I find that it makes it much easier. And I'm also using Helm in order to install my instance of Karpenter onto my cluster, but I'm also doing that with Terraform. And I've added the relevant documentation in the links below, so I hope that will help you. Those are the main prerequisites to get started. Once you've done that, the next thing is to deploy what is known as the provisioner file, which is what we're looking at right now in my VS Code editor. And the provisioner file is a custom resource definition that details all the configuration specifications and is how you would apply any parameters such as the node types, any labels you want to apply, any taints, tags, or custom kubelet configurations. And as you can see over here as well, any hard resource limits that you want Karpenter to be aware of when it's creating new instances. And so in my situation, you'll see under requirements that I've specified that I want to make use of both spot instances and on-demand EC2 instances. And below here, under the provider section, this is very important, especially for Karpenter, to discover certain resources in your AWS environment so that it's aware of where it can spin up the relevant resources. So in this case, if you see that there is the subnet selector and the security group selector, I have applied certain key value pairs, which are essentially my tags attached to the relevant subnets, and a security group that has the relevant tag as well. And Karpenter will be able to discover them when it is communicating with these particular resources so that it can provision the additional compute resources. So when you've got your Kubernetes cluster running in AWS and you've got Karpenter installed, the next thing is to deploy your provisioner manifest file. And I've already done that. So I'm going to jump ahead. And the next thing that we're going to look at is the current layout of nodes that I have in my cluster. And the reason I want you to see this is so that you'll be able to watch the process of Karpenter actually provisioning an additional instance in my cluster based on the requirements that will be specified in my pod, or my deployment resource rather. So I've got 4 nodes running at this particular point in time. The next thing that I want to do is deploy a deployment resource. And so I'm going to open this up over here. And this deployment resource is the same one that's actually available in the Karpenter documentation. The main change that I have made is under the spec configurations. And this is where I'm detailing the affinity rules. So you'll notice under spec, we've got affinity, and this is very similar to the node affinity rules that you would be applying. In this case, obviously, we're working with pod affinity. And as I mentioned earlier, similar to node affinity, you can apply this in either a hard or soft approach, depending on the rule that you apply. And there are 2 rules. So in this case, it is required during scheduling, ignored during execution. The alternative would be preferred. And so this is the strict or hard rule that we're applying. And so I want all of this to be taken into consideration by the scheduler when it is looking at the different compute resources I have available to me, and it wants to deploy pods for this particular application. So I've got 8 replicas that need to be scheduled. Now, in addition to that, very important is the topology. And so you'll see under here, I've got my topology key, and I am using a zone. So that means that my availability zone is what is going to be considered, is what is going to make up the entire topology for my particular infrastructure. So I want all of these pods to be placed in close proximity, and that proximity is determined by the topology, which in this case is an availability zone. The other key value pairs over here are basically your bread and butter that you would be making use of on any other deployment resource where you want it to know which pods it should actually be managing. So what I'm going to do now is actually create this. And so I'm just going to quickly open up my terminal. I'm going to come here. I'm going to create this, and we'll see these pods getting spun up. I'm going to have a look at these in K9s because I think it's a little easier to view, and you can see already there's an additional node that is getting created by Karpenter. But I just wanted you to see some of these pods that are in a pending state, and so Karpenter is essentially watching them. If you want to have a quick look at the logs, I'm going to hit L over there. And you can see Karpenter is going to work, and you can see some of the different logs over here, just the processes in terms of it discovering a particular EC2 instance type, it discovering zonal offerings as well, and the relevant subnets and the security groups. Just thinking back to some of the things that I mentioned, you can see it's created the launch template, and then it's actually launched the instance. So I'm going to go back to the nodes. And you'll see the one right at the bottom here is the one that's been created by Karpenter. And we're going to give it a little bit of time for it to get ready. And you'll see already that the scheduler has made the relevant decision for 8 of the pods to be scheduled there. So that's actually all of the replicas. There might be some scenarios in which the scheduler might only schedule, let's say, 6 pods to that particular node, and then the 2 other pods out of the 8 could be scheduled to other nodes, but that fall within the same topology based on the availability zone. So we can see the node is ready. The pods have already been scheduled. And so I'm just going to describe this. And you'll see, we can see the details of our node. You can see over there, instance type is T3 2x large. And if we come right at the bottom over here, this node has been provisioned in EU West 1B. So that's the particular availability zone. And so our requirements have been met because now all of our pods are all 8 pods. And I'm assuming that this is every one of the inflate pods, but the best way to actually check that is to come over here, run kubectl, get pods, and run this particular command where I want to see, and you can see over there that we have our pods running on these different instances. Oh, actually, take a look at this. So you'll see 221, the host with the IP 10.0.1.221 has 1, 2, 3, 4, 5, 6 pods for inflate. And so if I were to come back here, you'll notice that that's the one right at the bottom over there. So it's got 6 of the inflate pods, whereas 2 of the inflate pods have actually been scheduled to different instances, 118 and 168. And so I'm going to assume that those are all in availability zone EU West 1B, so that we still have our topology requirements met. But let's take a look at that. So 118 and 168. Hit the describe on this one, and you'll see over there, EU West 1B. And then lastly, this one over here, 168, EU West 1B. So this is perfect because that shows that even though 2 of the inflate pods were scheduled to different nodes, they still, our requirement, topology requirement to be specific, has still been met because they're all in the same availability zone, which meets our pod affinity rules. And in addition to that, Karpenter essentially spun up a node that was still able to meet all of our resource requirements or demands based on this particular spec over here. So the next thing that we're going to do is we're going to look at the anti-affinity rule. All right, so I have deleted the last deployment resource for the inflate application, and Karpenter detected that, and in response, it downsized my compute resources by deleting the node that had been provisioned. You can see over here the host name that ended with the IP, I think it was 122, has now been deleted. So we've gone back to 4 nodes, which is perfect for the next step, which is going to be anti-affinity. I'm working with the exact same application. The deployment resource is very similar. The main difference is going to be under the spec configuration. You'll notice under the affinity property, now it is pod anti-affinity. So basically, I want my pods to repel each other for increased availability, or essentially high availability, so there's no single point of failure for this particular application. And you'll notice that you can follow a weighted approach to this as well. And in addition to that, I'm with my particular topology key, very similar to the last one. I want to take a zonal approach. So that means that I want my pods to be spread across different availability zones. So just going back to the topic of high availability, in the case that one availability zone was to go down, I still want my application to remain available. Now, you'll notice that the rule that I'm taking in this case is a preferred approach, preferred during scheduling, ignored during execution. Previously, it was required, so this is the softer approach. And remember, I've got 8 replicas over here, so there's a high chance, especially with the preferred approach, that I will have multiple instances of my pods existing in the same availability zone, but I still want them to be spread across different AZs. So let me go ahead and create that, and we're going to see how Karpenter responds to this. It will provision a node. It might even be more nodes than this. And in addition to that, we want to see what the spread will actually look like. All right, so running into a couple of connectivity issues with K9s, but as you can see over here, this node that has just been alive for about 65 seconds is the new one that has been created by Karpenter. And as you can see over there, we had a number of pods that were in a pending state, but after the provision of this additional node, now we've got all of our pods that have been provisioned, as you can see, each one of the replicas. Now, the interesting thing that we want to take a look at is to see what the spread actually appears like in terms of how they've repelled each other and how the scheduler and Karpenter have worked together to give us higher availability across the topology, in which case it's multiple availability zones. So I'm going to come back to the terminal over here. And so this is each one of the replicas for the inflate pod. And if we take a look at the nodes over here, you'll notice that we've got some pods running on the same host. So 10.0.0.88. We've got pods there, 1, 2, 3, 4, 5. So we've got 5 pods on the same host. But then we also have pods on these other hosts over here, 118, 232, and 168. And so what I'm going to do now is I'm going to come back to K9S, and I'm hoping that I've overcome those connectivity issues. There we go. So what we want to look at now is we're going to see the availability zone for the node that was just created by Karpenter. So I'm going to describe that. This is an EU West 1A. And if I take a look at any one of the others, so if you come back here, just for clarity, 118 and 232 and 168. So 232. And that is an EU West 1A, so same availability zone. 168. And you'll see this one is an EU West 1B. So essentially our topology requirements and our pod affinity rules have been met in terms of the requirements and the constraints that we wanted to apply. And remember, I took a preferred approach in terms of the rule and how hard this should be applied. So that's an example of pod affinity and pod anti-affinity. Next up, we're going to look at volume topology awareness.
Next up, we're going to consider volume topology awareness. Before this feature was implemented in Kubernetes, the processes of scheduling pods to nodes and dynamically provisioning volumes were independent. As you can imagine, this introduced the challenge of unpredictable outcomes for your workloads. For example, you might create a persistent volume claim which will trigger the dynamic creation of a volume in a certain availability zone. For example, EU West 1A. Whereas the pod that needs to make use of the volume gets placed on a node in a separate availability zone. As a result, the pod will fail to start. This is essentially problematic for your stateful workloads that rely on storage volumes to provide persistence of data. It would be inefficient and counterintuitive to dynamic provisioning to manually provision the storage volumes in the appropriate availability zones. And that's where topology awareness comes in. Topology awareness complements dynamic provisioning by ensuring that pods are placed on the nodes that meet their topology requirements. In this case, storage volumes. Now, the goal of topology awareness scheduling is to provide alignment between your topology resources and your workloads, thus giving you a more reliable and predictable outcome. This is handled by the topology manager, a component of the kubelet agent running on your nodes. So this means the topology manager will make sure that your stateful workloads and the dynamically created persistent volumes are placed in the correct availability zones. In order to use volume topology awareness, ensure that you set the volume binding mode of your storage class to wait for first consumer. This property delays the provisioning of persistent volumes until a persistent volume claim is created by a pod that will actually use it. In scaling events, Karpenter, the scheduler, and the topology manager work well together. In combination, they optimize the process of provisioning the right compute resources and align the scheduled workloads with their dynamically created persistent volumes. These technologies enable you to run and reliably scale stateful workloads in multiple availability zones. You can then spread your applications or databases in your cluster across zones to prevent a single point of failure. So considering that EBS volumes are AZ specific, your workloads should be configured with node affinity to ensure that they are provisioned in the same AZ where they were first scheduled for a successful reattachment.
All right, so similar to the previous demo sections, just so you can see the nodes that I have existing at the moment, I got 4 in my cluster. Now I'm going to proceed to give you a quick overview of the stateful set that I'm going to be deploying. Right at the top here, we've got our service resource, which is for the stateful set application that will be created. As you can see, I'm working with my Express Node.js application that is usually my go-to example app, but we're more concerned about the stateful set, so we don't need to worry too much about the service. As you can see over here, I've got 20 replicas that are going to be created. Now, something that we need to understand, it's very important when it comes to working with stateful workloads. is you want to be able to spread these applications and databases in your cluster across different zones to prevent a single point of failure. Now, considering that EBS volumes in AWS are AZ specific, your workloads should be configured with node affinity to ensure that they are provisioned in the same availability zone where they were first scheduled for a successful reattachment. So you'll notice over here under the spec section, I've got my affinity property similar to the interprod affinity that I had in the previous examples, but now we're setting up node affinity, and I'm going with a strict rule, which is required during scheduling, ignore it during execution. And then for the node selector terms, you'll notice over here for the topology, I'm going with a zone approach, and specifically in availability zone EU West 1A. So that means that these 20 replicas should be provisioned in this particular availability zone. And the reason why we don't want to have multiple zones here is because if the scheduler schedules a particular pod on a node in a different availability zone, then you might run into issues with volume reattachment. So that means that, let's say it was initially scheduled in EU West 1A, and then that pod eventually dies because pods are ephemeral, but then it gets rescheduled in EU West 1B or EU West 1C, then it won't be able to reattach to the volume that was initially provisioned and attached to it when it was first created. So you want to be mindful of that particular kind of scenario. And right at the bottom over here, I've got my volume claim template, and you can see over there that my storage class name is GP2. So I've already got that set up from the moment that my cluster was created, but we can review it. And you'll see that there is my storage class, and I'm going to describe it. And something that you have to remember that is really important over here is the property for volume binding mode. And it has to be set for wait for first consumer so that you still have that dynamic provisioning and essentially have the delay to wait for the persistent volume claims to be created and then the persistent volumes to be attached appropriately. So now that we've covered that, I'm going to head over to the terminal and just create the stateful set. So as you can see over here, the first replica is being created. And if it's already past the process of the status rather of just pending, then that means that we've got our persistent volume claim that has actually been created and our persistent volume in addition to that. So you can see that the process is continuing and each one of these replicas are going to be created. But let's take a look at the persistent volume claims. And you can see over there that is bound. And so if I was to look at the persistent volumes, that will be created as well in response to each one of those PVCs that is being created. All of this is completely dynamic based on the template that I set up as well, and because of the property that I have inside of my storage class. So if I head back to pods, then this is essentially going to keep on going. This will continue until every one of my 20 replicas for the Express Node.js stateful applications gets created. But that essentially already demonstrates what I wanted to show you. The only thing that is left at this particular point would be to notice when we have essentially used up all of our resources with the existing computation that we have available to us. So let's see Karpenter come into play to provision a new node or nodes for us to make sure that we have exactly what we need, but we still fulfill the requirements for the volume topology awareness. So this is the node that has just been created by Karpenter, and you'll see that it is in the availability zone EU West 1A, and this is a T3 medium. Karpenter might create some additional nodes. We still have a bit of a way to go until all of the replicas get created. All right, and as you can see, all of our pod replicas have been created. If I was to switch over to have a look at the different nodes, we'll be able to see the ones that were provisioned most recently by Karpenter. And you can see over there, this node that has only been alive for about 98 seconds. And then we've got these that have been around for a couple of minutes. So that's 1, 2, 3, 4, 5, about 6 nodes that were provisioned by Karpenter. So the next thing that we actually want to do is to take a look at all of the nodes with a specific topology within EU West 1A. But just to bring it full circle, so the persistent volumes were all dynamically created in response to each claim from the stateful set replicas, and each one was created in the appropriate AZ, resulting in the successful creation of each pod replica. Otherwise, they would be stuck in a pending state. And in conjunction, Karpenter provisioned new nodes in the relevant availability zone to meet the compute requirements of the stateful sets. What I'm going to do right now is just one last kubectl command. As you can see over there, so just with the specific label topology.kubernetes.io, and the zone is for EU West 1A. I'm going to fetch that. And as you can see, all of our new nodes were created in this availability zone. So Karpenter provisioned nodes, and in doing so, it was still doing that in conjunction with the requirements that we had in place for our volume topology awareness. So that brings things full circle.
Thanks a lot for watching. If you found that helpful, hit the like button, subscribe to the channel, and stay tuned for more.